28.2 million tons. That's how much rock Swiss engineers ripped from the heart of the Alps to create a single tunnel. To visualize that number, imagine filling 13 Great Pyramids of Giza with crushed stone. Now picture all of it being hauled out through a hole barely wide enough to fit 2 train cars. This is the Gotthard Base Tunnel, and the story of how it came to exist pushes the boundaries of what humans can achieve when they refuse to accept limitations. At 57 kilometers, this is the longest and deepest traffic tunnel ever constructed. It runs 2,300 meters below the Alpine peaks, where the rock temperature exceeds 46 degrees Celsius, and the pressure from above can crush industrial steel like aluminum foil. Engineers didn't just drill through a mountain. They descended into an environment more hostile than most places on Earth, and they built a railway through it. Welcome to Project Scale. Today, we're going inside the world's deepest tunnel. The Alps have divided Europe for as long as humans have walked the continent. Ancient Romans built roads over the passes, losing countless soldiers to avalanches and exposure. Medieval merchants paid small fortunes to guides who knew the safe routes, and still many never arrived. For centuries, crossing the Alps meant risking death. The mountains were not a barrier you conquered. They were a force you survived. By the 1800s, the Industrial Revolution demanded a solution. Trade between northern and southern Europe was exploding, and the mountain passes couldn't handle the volume. The original Gotthard Rail Tunnel, completed in 1882, was celebrated as one of the greatest engineering achievements of its era. At 15 kilometers, it was the longest tunnel in the world. Swiss newspapers called it the eighth wonder of the modern age. But that triumph came soaked in blood. 199 workers died during the 11-year construction. Dynamite accidents, cave-ins, and a brutal disease called tunnel sickness claimed lives almost daily. Workers operated in near darkness, breathing air thick with rock dust, their lungs slowly filling with silica. Many who survived the construction died within years, their bodies destroyed by the conditions. The old tunnel served Europe for over a century, but by the 1980s it was clear that this engineering marvel had become a bottleneck. Here's where the story takes an unexpected turn. The original Gotthard Tunnel climbs over the mountains using a series of spiral tunnels and steep gradients. Trains had to slow to a crawl, using extra locomotives just to haul cargo up the inclines. Meanwhile, trucks were lining up for hours at the borders. The tunnel that once represented the peak of human achievement was now holding Europe back. In 1992, Swiss voters faced a decision that would define their nation for generations. The proposal was audacious: build an entirely new tunnel, but instead of going over the mountains, go straight under them. A flat-level railway that would allow high-speed trains to cross the Alps in 20 minutes. The cost estimate? Over 12 billion Swiss francs. The timeline? Nearly 2 decades. The Swiss said yes, but they had no idea what they were really voting for. The engineering challenges were unprecedented. The Alps aren't just tall, they're massive in a way that defies imagination. That 2,300 meters of rock above the tunnel creates pressures that can squeeze steel beams like wet clay. Engineers calculated that at the deepest point, the weight above each square meter of tunnel ceiling exceeded 60,000 tons. For context, that's roughly the weight of a fully loaded aircraft carrier pressing down on an area smaller than a parking space. Then there's the heat. The deeper you go into the Earth, the hotter it gets. This is called the geothermal gradient, and in the Alps, it means temperatures increase by about 25 degrees Celsius per kilometer of depth. At the tunnel's lowest point, the natural rock temperature exceeds 40 degrees Celsius. Workers would be operating in conditions similar to a brutal sauna, while handling heavy machinery, high-voltage electricity, and industrial explosives. And then there's the water. This is the challenge that nearly doomed the project. The Alps act like a giant sponge, holding billions of liters of groundwater in cracks, fissures, and underground rivers. When you drill into this rock, you're essentially puncturing a pressurized water system. Engineers knew they would encounter water, but the volume exceeded all predictions. At some points, over 150 liters per second gushed into the tunnel from underground aquifers. That's enough to fill an Olympic swimming pool every 3 hours. Without constant pumping, the entire tunnel would have flooded within days. Remember those 28.2 million tons of excavated rock I mentioned at the start? Every single ton had to be hauled out through narrow access tunnels, while water was simultaneously being pumped out and workers were being rotated in. The logistics alone would have been impossible for most engineering teams on Earth. The solution was elegant in its complexity. Instead of drilling from two ends and meeting in the middle, engineers designed a construction approach using 4 tunnel boring machines attacking the mountain from multiple directions simultaneously. But even this wasn't enough. They built a network of access tunnels, vertical shafts, and underground staging areas that essentially created a small city inside the mountain. The tunnel boring machines themselves were engineering marvels. Each TBM stretched over 400 meters long and weighed 3,000 tons. The cutting head measured 9 meters in diameter, studded with 85 tungsten carbide disc cutters that could slice through solid granite. These machines didn't just drill. They installed the concrete tunnel lining as they advanced, creating a finished railway tube inch by inch. At peak efficiency, a TBM could advance 25 to 30 meters in a single day. That might sound impressive until you remember the tunnel is 57 kilometers long. At that rate, each machine would take over 5 years just to drill its section, assuming nothing went wrong. Things went wrong constantly. The Alpine geology is notoriously unpredictable. One section might be solid granite, perfect for the TBMs. The next might be fractured gneiss that crumbles at the touch. Some areas contained massive amounts of crystalline quartz that destroyed the disc cutters in hours. Other sections were so soft that the tunnel walls would start collapsing before the concrete lining could be installed. For the worst sections, engineers had to abandon the TBMs entirely and resort to a much older technique: drilling and blasting. Workers would drill dozens of holes into the rock face, carefully pack them with industrial explosives, and detonate controlled blasts that shattered a few meters of rock at a time. After each blast, crews would rush in to clear the rubble and install temporary supports before the next section could collapse. It was slow, dangerous, and exhausting work, but sometimes the old methods are the only methods that work. Those 199 workers who died building the original Gotthard Tunnel in the 1880s used the same basic technique. The difference was that modern safety protocols, better equipment, and strict regulations kept casualties far lower than anyone expected. Speaking of the workers. At the peak of construction, 2,400 people worked on the tunnel simultaneously. Over the entire 17-year construction period, the total workforce exceeded 10,000 workers from over 20 different countries. They worked in shifts around the clock, 24 hours a day, 365 days a year, Christmas, New Year's, national holidays. The tunnel never stopped. The heat was relentless. At the deepest work sites, even with massive industrial cooling systems pumping chilled air from the surface, temperatures in the work areas regularly exceeded 35 degrees Celsius. Workers could only spend a few hours at a time at the tunnel face before being rotated out. Heat exhaustion and dehydration were constant threats. Medical teams were stationed underground permanently, treating everything from minor burns to cardiac events. 9 workers lost their lives during the construction. Each death was a tragedy. But compared to the 199 who died building the original tunnel, modern safety engineering had made an enormous difference. Every worker wore multiple sensors monitoring heart rate, body temperature, and air quality. Escape routes were drilled parallel to the main tunnels. Emergency shelters with independent air supplies were installed every 325 meters. The precision required for this project defies belief. The tunnel was being drilled from multiple directions, with the sections needing to align perfectly when they met in the middle. We're talking about drilling through 57 kilometers of unpredictable geology while maintaining an alignment accurate to within centimeters. The breakthrough moment came on October 15, 2010. After 8 years of drilling from opposite directions, the eastern and western tunnel sections were about to meet. Engineers had calculated that the alignment error would be no more than 8 centimeters, which was already considered remarkably precise for a tunnel of this length. When the final blast broke through and the dust cleared, workers from both sides could see each other's lights through the gap. The actual alignment error? Just 2 centimeters horizontally and 1 centimeter vertically. Over a distance of 57 kilometers, that's the equivalent of shooting an arrow from one side of a football field and hitting a target the size of a small coin on the other side. The celebration was emotional but brief. Connecting the tunnel sections was just the beginning. The next 6 years would be spent installing railway systems, electrical infrastructure, ventilation networks, safety equipment, and conducting thousands of test runs. The completed tunnel is actually 2 parallel tubes, each carrying a single track in one direction. This design allows for safer operation and easier maintenance. If one tube needs emergency repairs, trains can still operate through the other. Between the tubes, cross passages connect every 325 meters, providing escape routes and access for emergency services. 2 multifunction stations, essentially complete underground railway stations built inside the mountain, allow trains to switch between tubes and provide staging areas for rescue operations. The ventilation system can completely exchange all the air in the 57-kilometer tunnel in just 20 minutes. In case of fire, massive fans can control smoke direction, keeping escape routes clear while emergency services approach from the opposite direction. The tunnel is equipped with its own fire brigade, its own medical facilities, and enough emergency supplies to support hundreds of people for days if necessary. Remember that geothermal heat that made construction so dangerous? Engineers turned it into an advantage. The warm groundwater that flows into the tunnel is now captured and used to heat hundreds of homes in nearby communities. What was once a threat became a resource. That's the kind of thinking that made this project possible. On June 1, 2016, the Gotthard Base Tunnel officially opened. European leaders gathered for a ceremony that felt more like the dedication of a monument than the opening of a transportation route. The first passenger service began on December 11th of that year. The impact has been transformative. Travel time between Zurich and Milan dropped from over 4 hours to around 2 hours and 40 minutes. Freight trains that once struggled up steep gradients, burning massive amounts of fuel and requiring multiple locomotives, can now pull longer, heavier loads through the flat tunnel using a fraction of the energy. The flat profile is actually one of the tunnel's greatest technical achievements. The old mountain route had gradients up to 2.6%, steep enough that trains needed extra locomotives just to climb the hills. The base tunnel's maximum gradient is just 0.8%. Essentially flat by railway standards. This means trains use less energy, travel faster, and can carry significantly more cargo. Since opening, over 50 million passengers have passed through the tunnel. Freight traffic on the corridor has increased by more than 20%. Every ton of cargo that moves by rail instead of truck reduces carbon emissions by approximately 80%. The Swiss essentially built a green superhighway through the most formidable mountain range in Europe. The total cost reached 12.2 billion Swiss francs, roughly 13 billion US dollars at current exchange rates. That works out to about $228 million per kilometer. Expensive by any measure, but the Swiss voted for this project twice, confirming their commitment even as costs rose beyond initial estimates. They understood that some investments paid dividends for generations. The Gotthard Base Tunnel is the centerpiece of a larger vision called NRLA, the new railway link through the Alps. This network includes the Gotthard Base Tunnel, opened in 2007, and the Scenery Base Tunnel, completed in 2020. Together, these tunnels are creating a high-speed rail corridor that will eventually connect the ports of the North Sea to the Mediterranean. But the Gotthard stands as the crown jewel, a monument not just to Swiss engineering, but to human determination itself. Consider what this project represents. 57 kilometers through solid rock, 17 years of continuous construction, 28 million tons of excavated stone, 4 million cubic meters of concrete, temperatures that could kill an unprotected person in hours, pressures that could crush industrial equipment, water flows that could flood the entire tunnel in days, And through it all, thousands of workers from dozens of countries, speaking different languages, practicing different trades, came together to achieve something that previous generations would have considered impossible. When passengers board a train in Zurich today, they settle into their seats, open their laptops, and barely notice as the train descends into the mountain. 20 minutes later, they emerge in southern Switzerland, the Alps now behind them. Above their heads, hikers traverse the same peaks that have blocked travelers for millennia. The mountains haven't moved. We just found a way under them. The engineers who designed this tunnel, the workers who built it, and the citizens who voted to fund it all shared something essential: the refusal to accept that a problem was unsolvable. They looked at the most formidable mountain range in Europe and saw not a barrier, but a challenge waiting for a solution. That's the power of engineering at scale. Not just building things, but reshaping the relationship between humanity and the natural world. Not conquering mountains, but finding paths through them that previous generations couldn't imagine. Somewhere deep beneath the Alps right now, a train is carrying passengers who will never know the names of the workers who made their journey possible. They'll arrive at their destination on time, check their phones, and move on with their day. But the tunnel will remain, carrying millions more, year after year, decade after decade. Some engineering projects solve problems. The Gotthard Base Tunnel changed what was possible. What do you think? Would you ride a train 2,300 meters below the surface of the Earth? Or does knowing the full story of what it took to build this tunnel make you appreciate the journey even more? Let me know your thoughts in the comments below. But the tunnel will remain, carrying millions more, year after year, decade after decade. Some engineering projects solve problems. The Gotthard Base Tunnel changed what was possible. What do you think? Would you ride a train 2,300 meters below the surface of the Earth? Or does knowing the full story of what it took to build this tunnel make you appreciate the journey even more? Let me know your thoughts in the comments below.